All right, and welcome back to some more stoichiometry. Back in topic 2, we learned about a lot of different mole conversions, and molarity was one of them. So I want to review molarity real quick before we get into our next problem. Molarity, which is indicated by a capital M as far as units go, is simply a concentration. It's telling you how concentrated a solution is, and it's one of several, but molarity is the primary one that we're going to be looking at here. And molarity is actually it's an equation that you can use to solve for the molarity of something by taking the moles of solute divided by the liters of solution. There's some example problems down here, but we're going to actually do example problems in topic 10 for this, so I'm going to skip those. But I want to point out right now what molarity actually is and how it can be used. So if you were reading on the bottle of, let's say, hydrochloric acid, and it reported that it was 6 molar, okay, that capital M stands for molar, which is the same thing as molarity. Well, what does that mean? That actually breaks out into, there are going to be 6 moles of hydrochloric acid for every 1 liter of solution. And a lot of times, since we're working in chemistry, we don't usually use liters, we usually say milliliters, and so that's the equivalent of 1,000 milliliters, right? But that's what molarity is. And so you can see that we can actually use molarity as a conversion to get from volume into moles. And so you're going to see an example of that in the next stoichiometry problem that we do. So let's take a look at example number 8 right here. In the lab, you mix 2 aqueous solutions, 0.200 molar calcium chloride and 0.250 molar sodium carbonate. If you delivered 14.53 milliliters of calcium chloride and 17.28 milliliters of sodium carbonate, and then it asks you some questions here, right? So let's go ahead and I'm going to actually pause the video. What I want you to do is do the first part, which is I want you to write the molecular, the ionic, and the net ionic equation. This is a review from the previous section that we went over, 9.3. So see if you can do that, and then resume the video, and we'll move on to the next part of the problem. All right, so we go ahead and have our answers there on the screen. The molecular equation is given there. Notice how all of the compounds are written correctly, especially the compounds that we predicted as products on the right side. The NaCl is the aqueous, the calcium carbonates are solid, or it's our precipitate. Take a moment and look at your ionic equation. Make sure that you have the ion written correctly, the correct quantity, the correct charge. Make sure you have aqueous after every ion, keeping calcium carbonate together. And then finally the net ionic equation down here. Now that takes up a lot of space, so for the remainder of the problem, we're going to actually go ahead and go on to the next slide, which is blank, and ask to solve for the second question, which is solve for how much of the precipitate you would form. Okay, so we're going to go on the next slide here and look at the remainder of the problem. All right, so I have the quantities written. It tells us that we had 14.53 milliliters of the calcium chloride, 17.28 milliliters of the sodium carbonate, and the question was asking how much of the precipitate is going to be formed. Notice it doesn't tell you what compound specifically, it just says the precipitate. It's up to you to know, okay, the calcium carbonate's the solid, and therefore that's what we're solving for. Now it didn't actually say a unit, it just said how much. Since it's a solid, it's assumed to be grams, right? So it should probably say how many grams of the precipitate, but it's common to say how much and to know that it's grams when it's a solid. One thing I forgot to bring over, and I'm going to do that now, is we do need to know the molarities. We need to know the concentrations of those aqueous solutions. All right, so the first one is 0.200 molar, and then the second one is 0.250 molar. I'm going to make sure I wrote those down correctly. Yes, I did. Okay, so from this quantity of reactant, I need to figure out how much solid can be created. And then from this quantity of reactant, how much solid can be created. So that's what we have to do to figure out what the limiting reactant is. And so ignoring the sodium carbonate for a second, I'm going to just solely zero in on that calcium chloride and say, okay, if I used up all of that calcium chloride, how much solid can I create? So the first step of stoichiometry, after you have the balanced equation, of course, is to take what you're given, convert it to moles. I have 14.53 milliliters. How am I going to get that converted to moles? Well, this is an aqueous solution. So the way we do it is we use our molarity. The molarity is going to serve as a conversion factor. So what I'm going to do is I'm going to write down what I'm given. Okay, so 14.53 milliliters of the calcium chloride. And then what I'm going to do over here is I'm going to use my molarity. So 1 liter, and I'm writing it like this is on purpose, 1 liter of solution will contain 0.200 moles of the calcium chloride. Now, liters is not going to cancel out milliliters, right? So rather than say 0.200 moles for every 1 liter, that's the same thing as saying 0.200 moles for every 1,000 milliliters, right? So that way the milliliters will cancel out, okay? And so this right here is my first step of stoichiometry. I was able to use this molarity to convert from a volume into a number of moles. The next step is I want to use my mole ratio. So what am I in moles in currently? I'm currently in moles of the calcium chloride, CaCl2, but I want to solve for calcium carbonate. And so that's going to be the moles that I put on top. And this is where we're going to use our balanced chemical equation. For every 1 mole of calcium chloride used, 1 mole of calcium carbonate will get produced. So that's nice and easy. It's a 1-to-1 ratio. So moles will cancel out there, and now I'm in moles of calcium carbonate. But I don't want to know moles of calcium carbonate. I want to know grams of calcium carbonate. So how am I going to go from moles of calcium carbonate into grams? We're going to use our molar mass. And so we need to figure out, for every 1 mole of calcium carbonate, how many grams is that? Okay, so I'm going to grab my calculator here. Calcium is 40.08, carbon is 12.01, oxygen is 16, but we have 3 of them, so that's 48. So if I add that up, my molar mass for calcium carbonate is approximately 100.09 grams. When I do that, my moles of calcium carbonate will cancel out, and now I'm in grams. Now before I calculate the final answer, I want you to see what we did here. This right here was step 1 of stoichiometry, convert to moles. This right here was step 2, use the mole ratio. And this right here was step 3. We just did that to convert to a desired unit, which was grams. It's always the same 3 steps with stoichiometry. So, with that being said, let's figure out what our answer would be just for this part right here. Alright, it looks like if I were to use up all of the calcium chloride, the maximum amount of precipitate I can create using 3 sig figs. Notice it's 3 because of the molarity, right? So 3 sig figs, 0.291 grams of calcium carbonate. Now that might not be my final answer yet. I don't know, because that was assuming we use up all the calcium chloride, meaning that's the limiting reactant. I still have to do that for sodium carbonate. So now, essentially I just figured out how many sandwiches I can make from all the bread. Now I need to figure out how many sandwiches I can make if I use up all the cheese. So it's going to look really similar, but now I'm going to use the information for the second reactant, the sodium carbonate. So 17.28 milliliters of Na2CO3. And you're going to see it's very similar. So for every 1,000 milliliters, which is the same thing as 1 liter, it will contain 0.250 moles. All right, so that gets rid of my milliliters. And that, like I said, is step number 1 of stoichiometry. Next step, I'm going to use my mole ratio. So I want to get out of moles of the sodium carbonate, and I'm still solving for calcium carbonate. I'm not solving for anything else. I'm still trying to figure out how much precipitate can be formed. And for every 1 mole of sodium carbonate, 1 mole of calcium carbonate is produced. So once again, a 1-to-1 ratio. That's just a coincidence. That doesn't always happen. So I want to make sure that that's clear. You still have to do the mole ratio. Make sure you show that step. So that's step 2. Finally, I don't want, and let me cross out these moles here. I don't want moles of calcium carbonate. I want grams. But now that I'm in moles of calcium carbonate, which is what I was up here, this last step is going to be the exact same thing because I'm already in moles of calcium carbonate. So I don't have to recalculate what that molar mass is going to be. It's still going to be the same. So step 3 is going to be the same for both. You know, it's never going to change because at that point you're in the same compound. So step 3 is converting to your desired unit. So let's see what we get when we calculate that. Once again, 3 sig figs. All right, and when I calculate that, I end up getting 0.432 grams of calcium carbonate. So what I just did is I said, hey, if I use up all the bread, how many sandwiches can I make? If I use up all the cheese, how many sandwiches can I make? Out of those two, the one that is the most is not realistic. This is the one that you're actually going to create. So in all reality, you will produce 0.291 grams of calcium carbonate. More specifically, what was the limiting reactant? What dictated how much product was created? It was the calcium chloride, right? So the calcium chloride limited our production of precipitate, meaning sodium carbonate was the excess reactant. Excess meaning there's going to be some of that reactant left over. So to solve for our last question, and if I go back real quick on the slide just so you can see it, okay, we were looking, so we solved for number 2. The last question, number 3, draw the beaker drawings, and it says, no, pay attention to the last beaker. So I have that on the screen here. I've got the chemical equation there at the top. I've labeled the limiting reactant and the excess reactant. So now I want to actually draw the beaker drawings. What would those look like? So in this first beaker drawing, we're just simply taking this first reactant and we're just breaking it apart. Nothing new here. So you'd have the calcium ion and the 2 chlorine ions. In this second beaker, you'd have the second reactant broken up. And so I'd have those 2 sodium ions and then that 1 carbonate ion. And then in this final beaker, this is what gets tricky. Okay, so this is what I would want you to do. First of all, ignore anything about limiting and excess. Forget about it for just a moment. You need to draw these products in the beaker, okay? Because those are the 2 things that get created. So the very first thing I draw, okay, we've got our precipitate that's at the bottom. So that calcium carbonate, notice I put it all together, leave it together because it's the solid. Then I have the 2 sodiums and the 2 chlorines. Those are my spectator ions. So regardless of whether or not there was a limiting reactant or an excess reactant, let's assume you had just enough reactants of both, that they both got used up. There was nothing left over, there was nothing excess, they both got used up. This is still what you would have in your final beaker. That's like saying, okay, I have no bread left over, I have no cheese left over. Sandwiches, that's the only product. But we know in reality there was an excess reactant, right? There was something left over. This sodium carbonate was the excess reactant. And so I need to also represent that in the final beaker. So in addition to product 1 and product 2, you also have a little bit of excess reactant. And I'm going to draw it in a different color just so you can see. You have the 2 sodiums, because it was 2 sodiums here, and then the carbonate. What I'm writing in pink is the excess reactant. So by drawing that in there, I'm showing, hey, not only do I have the precipitate and then the spectator ions, which are represented there, but also you have the excess reactant. Whatever's the excess reactant would also be shown in there. Sometimes students ask the question, well, you have 2 sodiums here and 2 sodiums there. Can I just combine them and make them 4? You can, but I'm asking that you don't, just because it's easier for me to see if you keep them separated. But you're not wrong if you did. Not wrong at all. But make sure the quantities are correct. You either have them split out 2 and 2, or you combine it to 4. All right. Let's see. I'm going to see if I can get through this last bit in the last minute. Reaction yields is the last item I want to talk about. In fact, you know what? I'm going to run out of time. We'll talk about reaction yields in the next video. It'll be a short video.